Yes. All right. I did start the recording. In case. All right. In case means who is missing to the body? Yeah, and I didn't see Renzo for a while, so I don't even know he's around. So only Brody is missing. If Brody were listening, I was talking about exam three. So exam three take home section or part two of exam three is due today, and I was talking about the final exam as well. So the final exam is due on week 15. So let me write it here. So final exam is take home due week 15 day 2. Okay, available week 14, sorry, week 14 day 3. So this is about the final exam, and exam 3 is take home only, no in class for final exam. All right, so what else? The syllabus for final exam, chapter 15 and 16. We are dealing with chapter 15 now. I have chapter 16 as well. Chapter 15 and chapter 16. Chapter 16, not that much that we're going to cover. Chapter 15, we are covering momentum and impact. You have seen it right already. And exam 3 was like chapter 14, right? The energy. All right, so chapter 15, we would be doing so many problems. This is problem number 3 that you're seeing here. I have 2 problems for chapter 15 today to cover. See how much we can do. And on Friday, when we come back, another 2 problems, and then we'll have 2 more weeks, approximately 1.5, I'd say. That's enough for chapter 16. And chapter 16, I won't be covering that much. A little bit of theory and some math problem, okay? Any question? Okay, perfect. All right, let's do this math. Let me get my class note as well. All right, so my class note is here. Let's talk about the problem. So what you're seeing here on the problem, we have a spring attached with this block A, and there is a block B. Initially, block B is moving at this speed minus. Why I said minus, because the x and y direction is this direction. So minus 15 meter per second, right? So opposite to x direction, that's why. And block A is an standstill, means it doesn't have any velocity initially. So that's the info is given here. So 2 velocities and 2 masses for these 2 blocks. And obviously you see this block A is attached to the spring of 10 Newton kilonewton per minute meter. That's the stiffness of spring. Now what happened when this block A is coming to block B, block B is coming to block A, there would be impact, obviously, right? So once there is an impact, there will be new momentum, right? Means the velocity is going to change for both of them. What do you expect after that? You would be expecting definitely same velocity if those are attached together. If those pump and goes back, then it be different velocity, assuming both goes together, right? Did I upload chapter 15 material in Brightspace yet? I should. Okay, so and there is chapter. These materials should be in Brightspace. What you're seeing here. Okay, just dig through it a little bit. So we can let me talk a little bit more. What we're gonna find? We're gonna find the compression of the spring. What is saying here? You see, these 2 hooks will join when block B will gonna come and hit block A, and both of them will gonna be as like act like one object, right? So these 2 blocks will gonna attach together. This is my A, this is my B, and they all gonna move in this direction, right? And now initially our spring was located at a certain position, right? And then it will gonna have this compression happen, right? So if this is your X and this is your, say like this is your x1, this amount of compression happen, maximum amount of compression happen will gonna be x minus x1. Okay, That's what we're trying to find. I mean, visually, I'm trying to represent what is showing here. You understand it, right, Arlene? So the spring get compressed. So like how much of the compression happened, bottom line, that's what they are asking. They give you the mass for these two blocks. They give you the initial velocity. They said like, okay, block A is not moving, zero velocity. Block B is moving at minus 15 meter per second, right? Opposite to minus x direction, opposite to, sorry, minus x direction, in minus x direction. And then after the impact, the spring get obviously compressed. How much of that compression happened? So that's the question. All right, so we can consider both block as a single system, apply the conservation of linear momentum. What does it mean? You have to understand first momentum. What is momentum? Momentum means mass into velocity, right? So before impact, after impact, if the conservation of momentum happens, right, Joe? So what will happen before impact? You have this mass multiplied velocity for these two blocks separately. We're adding them up, right? That's the momentum. And after the impact, you see the mass for both of them together multiplied the velocity should be the momentum for after the impact. So bottom line here, they're saying, see, before the impact and after the impact, the momentum is going to get conserved. Conserved means nothing will going to get loose, nothing will going to get added. Whatever is there before, after there should be same, but it will going to just act differently. Means no momentum get destroyed. Bottom line, that's what they're saying. Okay, that should be your strategy to solve this problem. The other one, once you have that velocity, you see that goal, the first strategy or first step would be finding the velocity, right, after the impact, as if like, what would be the velocity here? It makes sense? The velocity v2, and as if like, you have the initial velocity, say like va1 is 0 and vb1 is minus 15 meter per second, right? So then step one is saying, okay, you do the momentum. I'm going to write it in formal fashion just shortly. So step one says, okay, you do that. MB, BV1, and it should be equal this two weight. So these two mass, MA, MB, right? And this V2. So they said like, okay, find the V2, the final velocity, right? And once you have that velocity, what you're going to do with that? That's the second step, energy conservation. Okay, to find the compression of the spring. We have done the energy conservation already, right? So energy conservation would be what? Kinetic and potential energy before and after the collision, right? Remember, what is the kinetic and potential energy before and after? Anytime you have the kinetic energy, that means like the half of mv squared. Remember that kinetic energy, half of mv squared. So before the impact, right, you have these two blocks, half of mv squared. Now this m is like ma and mb, two blocks, right? And the velocity will be different as well. Like the one is not moving, other one is moving at minus 15. Understand? So that's the before the impact. And after the impact, you have a new velocity and all sorts of things. That's the right side. Okay. Left side is like that. And initial potential energy is what? Initially the spring doesn't do that much, right? And those are sitting on a surface, and normal force kind of nullifying that. So it doesn't really have that much of potential energy effect, right? Initially, but after the impact, you see what happened? The spring get compressed, right? So if the spring get compressed, there's a potential energy for the spring as well, right? Anybody remember the equation for potential energy for spring? Half of x is squared, and x is the x is like kind of generic thing. Here the x is referring to the amount of compression or extension happen on the spring. In our case, it is like x1 minus x, right? That's the amount of compression. Can you please do the problem by yourself? Should be right. Based on this, what I said, but don't worry, I'm gonna go through the formal way of solving the problem. If there is no more question, I'm gonna start solving it. Any question? Everything's good? Okay, obviously I'm going to take out everything because I'm going to go really formal approach. Okay, so let's start with givens. I'm going to write the givens here, okay? So more space for you to see better. So BA and BV, those are two velocities. Those are givens, right? So now you can say them like, VA1 or VA0 or VA final, whatever subscript you want to put. I don't know. I would like to put 1. And I would like to say, what is the velocity for block A? Anybody remember it's 0, right? And block B is negative 15. How do I write negative 15? You see my x and y convention? That's the convention that I use. Joe, you may use a different way, right? You may say, you may use the y is opposite to the direction of y, and x is opposite to direction of x. It really doesn't matter which way you are thinking, right? Ultimately, it'll gonna give you the same solution. And the k, what is k again? People use k for what? Spring constant. So you may want to write it here one more time. Spring constant. So the k value is 10 kilonewton per meter, right? All right, so that's what given. And then obviously you have to deal with everything in base unit. So you should be changing them to Newton per meter, right? And then you have these two steps, right? First one is the conservation of linear momentum. Another one is the conservation of energy, right? So dealing with those two steps, you can say like find max spring compression, right? You can say S max. You can say this one is S max, right? But these are notes only, but this is the formal way of writing what I just wrote here, like S max. Again, S max is what? The amount of compression happen on the spring, right? We got it? Joe got it so far? Taking class notes as well? All right, perfect. So then solution. You have these two steps, right? The first one is the conservation of momentum. That's what linear momentum, you can say that. So conservation of, you guys are familiar with any other momentum? I had it here, linear momentum. I heard about angular momentum. You heard about it? Conservation of angular momentum? No? It's not linear. Just you can use the convention of r theta, right? R is the radius, theta is the angle. So the angular momentum, you can do the conservation of angular momentum. It's a little complex. It's not solvable. It's not like not solvable. It's like math, a little bit difficult math, right? But linear momentum is straightforward. X and Y direction, Cartesian coordinates. We are all happy, right? You guys learn about the polar coordinate, right? Cylindrical coordinate. Those coordinates are out there as well. Those goes with that way. Anyway, conservation of linear momentum. So on conservation of linear momentum, you have this left side. Okay, mi vi, and you can say I equal to 1 to n. Now in this case, n equal to 2, right? How many blocks we have? 2. N should be, in this case, number of blocks. Do you understand? Number of blocks, right? All right, perfect. So then it should be equal to what? Summation of I1 to n again, then mi vi. Now it could be a little confusing. You should be saying 1 and 2, right, as a subscript. You know what I'm saying? The mass is not definitely changing. It's the velocity which is changing initially and after, right? Alina got it so far? What I did? I wrote the conservation of momentum. Left side, at the mass multiplied velocity. The summation sign is for what? I have 2 blocks, right? That's why I have the summation sign. Didn't you got it? On the right side, what we have? The final velocities, right? I was talking about it, showing the equation before. I just wrote it in a little bit formal way. Okay, so let me start giving you a little bit more. So here in these two ends, we can write this one is for before the impact. This one is for after the impact. If this bothers you, like the way I'm writing it, it feels like a jargon, like mathematical jargon to you, right? Then you can just simply write, the mass, ma multiplied the initial velocity plus mass mb multiplied initial velocity is equal mass ma block A multiplied by the final velocity, mass mb multiplied the final velocity. Everyone understand what I just said? In left side, before impact, initial velocities multiplied mass. Till you got it, right? In right side, you have what? Mass multiplied final velocities, right? That's straightforward. Okay, this is just a way of writing formally. All right, then the real thing will gonna appear, which I was just talking. So the mass, you have these two mass, right? Initially, you have ma and mb. I'm writing it this way first, so you will understand it better. So you have MA and MB, right? Okay, and then in both cases you have to multiply the velocities. So VA, VB, VA, VB, and you gotta put this thing subscript. Okay, 1 and 2 referring before and after the impact, right? I can write it this way. So 1 means before impact, 2 means after impact. Everybody understand? Are you taking notes? Take notes, take notes. All right, so now you know this is 0, straightforward. This one is what? Negative 15. And this one is MB. You want to write MB as MB for now? Or you want to plug the values? What is MB? I should have write it here. I didn't write it. So MA is 15. MB is 10. So I have this 10 kg. And then I have this 15. Okay, and then I have this I can write it this way on the notes here. So notes, what is the notes? This VA2 V2 should be same as V2. Why? Why do you think that I can write it? They couple together, they move together, right? They have a hook even. So they couple together, and we should have just one single velocity V2, and I should be writing it this way. So instead of that, I should be writing like V2 here, right? And then I should be writing like 10 kg multiplied V2. I should be doing the math and come up with the value of V2, which by the way, V2 should be like 15 plus 10. I'm just rewriting the same thing. I have this 10 kg here multiplied the 15. So there's the negative, right? Don't forget about the negative, and there's the reason behind that that you shouldn't forget. And then you should be finding the V2 value here. You should have like, this is 10, by the way. It looks a little different. So 10 multiplied what? Minus 15, and the unit is meter per second, and the velocity would be 6 meter per second, and there should be negative. What does this negative refer for, anybody? What does this negative mean? Exactly. So negative means after impact. You don't have to write it if you understand it. I'm just writing it for everyone. After impact, A plus B moved, block, you can say blocks, A plus B moved negative X direction, right? And again, this notes is for your understanding if you have issue of understanding. Now that's the first step. And now we have the velocities. After impact, what happened? What are we going to do after that? What's the goal? Finding the spring compression. And remember, and that's the chapter 14 concept, right? The conservation of energy. Like, the T1, V1, like, kinetic and potential energy before the impact. T2, V2, kinetic and potential energy after the impact. Alan, you got it? What I'm saying? Okay, take the class note. All right, so I may want to do a sketch as well. So you have these two different steps, right? Initially, at state 1 and state 2, I'm going to give you some time to take the class note, don't worry. So at state 1, you had this spring attached with this, right? And B just barely come here, right? It didn't start to move. It just come here. That's your state 1. Okay, I'm gonna explain this thing. So that's your V1. In this case, it's V2. I'm sorry. That's your V2, right? Everyone understand? So it's a little difficult to understand. focus on that. I mean, what happened? You see, initially one block is here, another block is there. That one is stand still, that one is coming to minus 50. Both come together, pump, right? So now, when they come together, what is the velocity initially? It has 6 meter per second, right? And that 6 is moving which direction? This way, right? Both of them are moving this way. Now, before it start move, like it has this velocity achieved, that what happened to the spring? The spring is stand still. It didn't got compressed at all. It is as it is, right? Does it make sense? But when they start to move, at some point, what will happen? You're going to push the spring, and suddenly both of them get stopped, right? Do you understand what I'm saying? So initially, both of them together, trying to move on -6 direction, 6 meter per second, and then they're going to move, try to compress the spring as much as it can, and at some point, they're going to get stopped, right? Both of them. Did you got it? And then what would be the velocity at that point when the spring gets stopped? Both of them get stopped. Zero velocity, right? But the spring now get compressed. So there are 3 states. Initially, one block B has -15, block A is stand still. Then at state 2, even though I said state 2 and 1 and 2 differently a little bit, but at state 2 means before the impact, both come together, wind up together, and get a velocity of -6 meter per second, and then they're going to still move. Finally, they're going to stop, and that would be the final compression. Okay, so those are your 2 different states. Okay, see if you understand that. And state 2 would be, so that's the compression happen. All right, so you see, initially, so that much of compression. So this is your X max. Remember S max? So that is the compression on the spring. And this again your block A and B. Block A and B. And now the velocity, the final velocity would be what? Velocity would be 0 here, right? Because that's where it gets stopped. Any question? Didn't you got it? All right, so the 2 block, let me give you some little bit of brief. So note here. So these 2 blocks compress the spring. Joe, you're not taking class note? And state 2, no velocity. All right, blocks are stand still. Take class note. I'm giving you some time because I don't have that much left, and I don't want to rush that much either. I mean, especially in today's class, I just have the math. I don't want to start a new problem. It's like 30 minutes, another 5 minutes probably take, and 5 minutes for you to take the class. So, yeah. This is a little challenging problem, right? So you are now dealing with both momentum and the conservation of energy, right? See, this class begins with what? Like the velocity, acceleration, the fundamental stuff you learned in physics class, right? And then slowly converted to the force, and then the energy, now the momentum, then the impact. Right? Those are the things actually. It's a summary of dynamics that you learned. Okay. Any questions so far? Everything's good? Do you guys need some more time to take the class note? Okay. Let me start dealing with this. So that's energy conservation. I'm going to write the equation for you, and I'm going to give you time to solve. Energy conservation. Remember the T and V, those sign. The V should be like, not velocity here in this case, the potential energy. Remember that, Joe? Okay, so then T1, V1 should be equal to T2, V2. Let's see if you understand. What would be the T2 value? It's 0. Why, Alyssa? The velocity is 0 because the spring get compressed. They can't move anymore, right? All right. So what would be the V1 value, Brad?
-6.
No, V, not the velocity. V1 is the potential energy at state 1 before impact. The capital V. That's tricky.
It would be
Before the impact, both blocks are together. They are not
zero.
Every zero, yeah. So before the impact, what happened? See, the impact happened, but the spring hasn't compressed yet. Now after that impact, now both of them are gonna get pushed. That's different story. But before, there's no compression on the spring, and obviously because of the normal push same as the mass of the weight, that's why there is no MGH for both of cases, right? So the spring, there's no way of contributing here on V1, right? But there is spring contribution here at V2. The T2 the same because they stopped. The T2, as I also said, like that would be zero as well, right? So now we have these two parameters here. We have this T1 here, which like the half of mv square, right? And this m would be what m? Like ma or mb or both? Both, right? Because both of them are together. Okay, and the velocity, what is the velocity, Arlen? Remember the velocity that we found? 6, right? So we know, this half of mv square, right? Did you got it? Half of mv square. M is again m1, ma plus mb, right? Christian, you got it? So, okay. So this v2 would be what? Christian, you remember the equation? Half of this v is the potential for spring, and that will be half of k s squared. This s that I was saying there, right? S max. You understand the S max, right? Everybody? So you got it? Can you solve it now? What's our goal? Find the S max. See if you can do that. All right. So I obviously what I was explaining so far. This would be 0. This would be 0. You can explain why those are 0 again, right? And the side note, I can write it here for reference only. Not necessarily you have to write it in actual sum. So see, like this T2 would be 0 because the spring stops at state 2, right? No movement. Okay, and then you can say V1 equal to 0, state 1, spring compression didn't start yet. And these are notes just for you to understand, not necessarily you have to write it the way I'm writing. You can write it in your own way, right? If you'd like to put it as reference. So now you can see that you have this half of what? The 2 looks a little weird, but it's half ma plus mb. And then this one would be v2. I did put a subscript v2. This could be confusing at state 1. So maybe let me see what I can do. Maybe you can write this one as VAB2. That way there won't be any confusion, right? So VAB2. AB is the both blocks are together now, right? Hopefully you understand it now, right, Joe? BAB2. So this is BAB2 square equal half of K. You know the K spring constant is given, right? S max square. All right, and I'm giving you the final answer. If you got the final answer, you can leave, but before you get the final answer, you have to done the math. So S max is equal 0.3 meter. And you got to understand what is S max means. Initially, if the spring is that big, it got a compression, right? And that much compression is S max, amount of compression. Hopefully you understand, right? You gotta do the steps, intermediate steps. Right? That's the final answer. So understand. And if you got the steps and everything, as I said, I don't have really time. I don't want to rush you because we are almost at the end of the syllabus. Okay. There's no point for me to rush at this point. Just have one more chapter left on the very minimum thing I'll cover on the last chapter. And this is the final chapter. You gotta understand, you really understand it solid. Okay. Okay. Don't worry, I'm gonna give you the steps. You can, if you have issues of solving or whatever. And to give you an nutshell, as a summary of this whole problem here, we did two steps here, right? The momentum, conservation of linear momentum, conservation of energy, right? So linear momentum is like before and after the impact, the mass and velocities, right? Combination of them. And conservation of energy tells us the kinetic and potential energy. Make sure you understand what is the potential energy. It's not necessarily mgh. It has the spring energy as well, which is half kx squared. And then we have to make sure we understand about the velocity, what's really happened, right? The spring initially doesn't move, so in left side T1 and V1, we had no velocity or T1 is 0. In right side, we had the movement, right? Sorry, right side it doesn't move, so sorry, I see the spring initially was moving, right? So on the left side we have the velocity get from the linear momentum. Right side spring got stopped, no movement, so velocity is 0. So that's why T1 is 0. Okay. However, in left side spring is not moving yet, so there is no potential. V1 is 0. In right side spring get compressed, so that's why half of k x square is there. We have to just find the value of the s. Okay. All right. You too. I'll see you all in no class on Wednesday. I'll see you all on Friday. Okay. Remember, I'm going to the conference. Okay. All right. Let me do the steps here. Don't worry, it doesn't. I have the steps, so you can match. So you have this half of 15 plus 10 minus 6 square. Yeah. So half of this 10,000 into Newton meter as max square. And if you're gonna do the math, you should have like this. So 75 multiplied 36 divided by 5,000. See, these two is gonna be 5,000. All right. So 6 square is 36. Okay. 150 divided by 2 is 75. And you're gonna do the square root, and this one would be in meter. That's the unit, right? And that should be your S max. And you should be finding the S max value as 0.3. Got it, Delina?